Good. Okay. So this is the first thing we noted about the electromagnetic waves, and then we went on to introduce the monochromatic waves. We discussed that those monochromatic waves didn't exist in practice, that we had to deal with the quasi-monochromatic waves, and then introducing the idea of the polarization fraction. Now, going back to purely monochromatic description, in the last lecture, I tried to condense this rather difficult topic, which is the response of a medium to a monochromatic wave. One thing, when you do the introductory courses in electromagnetics or electrodynamics or electricity magnetism, that monochromatic wave is really simple. But it turns out that when you go into the details, the math get quite complex. And I got a little bit lost here during the last lecture. So I just want to summarize very briefly what I'm trying to communicate here. So we have these constitutive relations. So these equations here on the left apply to the signal. This is all real, okay? Polarization, the induced polarization in medium, the current density, the magnetic field, and all these susceptibilities are all real. But when we go to a monochromatic component, we take the Fourier transform and in complex notation, okay? And each of these monochromatic components are spectral components, and they are we use the complex notation to describe them. So these are the spectra of the signal, and each of these is a complex quantity, and the proportionality coefficient is also complex. Now we can say that these complex these complex functions that relate B and H, etc., must be Hermitians, so that their counterpart in real space is real. Okay, so we have this hermeticity condition. Okay, so the other thing to note is that we have the convolution theorem. So let me write down the example here. So we're using the susceptibility as an example, the electric susceptibility. So we have the polarization is epsilon 0 chi of omega times E of omega. Okay. And then we apply, and we also know that in real space, P is epsilon 0 chi of E. Okay, and that's a Fourier pair. So we apply the convolution theorem, okay, and we learn that yes, well, what I've got here written in equation 55, which is basically that P of T, which would be the anti-Fourier transform of the spectrum, is the convolution of the anti-Fourier transforms of this inverse Fourier transform, I meant to say, of both of these quantities. So we have the convolution in time times yes, so this is 1/2 pi. This is the inverse Fourier transform of chi of omega. Okay. That would be what's called, I'm going to use another color here. So this would be, all of this is G of T minus T prime. Back to blue. And I've got, yes, so I need to, the exponent here is T minus T prime. times E of omega, E of t, which is also, well, it's not necessary to spell it out, E of t prime dt, times E of t prime, okay. So what I'm trying to say is that I'm applying the Fourier convolution theorem to this product. So we have this product of Fourier transforms, okay? And I'm saying that the inverse transform of the product is a convolution of the inverse transforms. So you see what I mean. And this part here is defined by as this quantity G, okay? So we have equation 55 in the end, where we define G of t as this simple connection with chi of omega. I got lost a little bit on that part in the last lecture, so I wanted to just summarize, because this part is rather simple, and we went on to make an example with a specific monochromatic signal. So this is a specific monochromatic wave. And we saw that in this case, we had the complex polarization, and that the electric susceptibility is connected to chi and the conductivity in this complex way. So things are not so simple once we go once we deal with a monochromatic wave that interact with the medium, okay? Now going back to what I was trying to explain right now, look at equation 63. This is where I got stuck last time, okay? And the way to recover it is simply take once again the inverse transform of this last equation. So I take the inverse transform, and I can write epsilon chi of omega is the integral from minus infinity to plus infinity in dt, that was over d omega, of g of t e I omega t. Okay, so this is the Fourier pair. And the trick here, according to the discussion we had last time, is to impose causality. And so if we impose causality, then I'll put it in red. So causality says that g of t is 0 if t is negative, for the arguments we exposed last time. And so this means that the limit of integration, we can restrict the limit of integration from 0 to plus infinity, since g of t is for negative t is null. Okay, so this is the main conclusion, because once we have this equation 63, what follows is a bit of difficult to digest a complex plane analytical calculus, but which is straightforward. This is the complex variable, and it's complex. But the physics stop here is what I'm trying to say. 63 condenses the physics, and from this relationship we can argue that then chi of omega is analytical in the complex superior plane, and go on with this reasoning to conclude these two equations, 67 and 68. So these are this p symbol here is principal value, and it is a limit on each side of the singularity we have in the denominator here. But the point is that the real part of the susceptibility is connected to its imaginary part, and vice versa. Okay, and we have similar relationships for mu and sigma. So now back to the more standard. This is all standard. Back to the more easy to use part of this topic. We use a plane electromagnetic wave, and remember that the wave number can be complex, we then have this type of behavior. So we have the imaginary part of the wave number accounts for extinction, and the real part is the oscillatory exponential here. Okay, and so we can obtain this dispersion relationship, and we define the complex refractive index. Okay, which is written this way, where epsilon and mu are both complex too. Okay, and so since n is complex, in the end, we can connect it to the real and imaginary parts of the wave number, and we have them replaced here. Okay, so where we have kappa would be the imaginary component of the refractive index, n is the real part. So this is well corresponded to the imaginary component of the component of the wave number, and this is what corresponds to the real component. Okay, and to finish, we have similar Kramers-Kronig relationships that connect the real and the imaginary parts of the wave numbers. Okay, so why is this really important to us? Well, because in astronomy, we have to deal with extinction all the time, and extinction then comes from this part, from the kappa. Now, how do we calculate the kappa? We calculate the kappa based on the other component, the real one. Okay, so as soon as you have the real part of the refractive index, we can calculate the kappa. Of course, we won't be applying this Kramers-Kronig relationship, but I thought it's important to know how this is done. Okay. So this was a brief summary for the previous chapter, and now we are going to introduce another complex topic, which is radiation, but that should be more familiar to you in general. Okay, so what we saw just now, I just reminded you, is that the electromagnetic potentials fulfill wave equations with the source term. Okay, and this can be generically written as equation 1. So that would be the wave equation with a source term for a component of the potential vector, or of the electric field, or of the magnetic field, or simply the electric potential. Okay, we have this type of generic equations, and this is what we want to solve. Okay, we want to calculate the resulting electromagnetic field due to a time-varying source function, which would be a time-varying charge density. Okay, and so, as you can guess, we'll be using the Fourier analysis. Okay, so this is the Fourier pair. Okay, again, this is how we write it in this case, not always, but we use this notation here. Okay, then we plug this into equation 1, and we reach the Helmholtz equation. So we already saw that last time as well. Okay, in the last chapter. Good. So this is what we'll be trying to solve in the Fourier domain, and then we take the inverse transform to get back to the time domain. Okay, so we're using the frequency time Fourier transform here. Okay, and so this equation 4 is very similar to the Poisson equation. Okay, Poisson equation has got a 0 on the right hand side, sorry, the Poisson equation, yes, that's correct. It's got 0. Yes, the Poisson equation is the same, but with a 0 here. And so we use similar machinery as for electrostatics. The idea is to introduce a green function. Okay, so this is a little bit scary sometimes when people talk about the green function. For the time being, we'll just be looking for a solution to equation 5. Okay, this is how we define the green function. Equation 4 is what we want to solve. Equation 5 is the equation for the associated green function. Okay, so what's the difference? Well, in this case, in equation 5, the source term is just a delta function. Okay. Now comes a little bit of algebra. We change coordinate system to this new variable r. Okay, so we have a new, well, this I should explain. The green function involves two variables, x and x prime. Okay, and we introduce, and these two variables comes out because we introduce the delta function here on the right hand side. Well, this I could also have used this other notation. Maybe it would have been simpler. What I'm trying to say is this: is that this is the Laplacian times k squared times j. And on the right-hand side, I could have simply written delta of x minus x prime. But the point is that since in equation 4, everything depends only on x, okay? This Laplacian acts only on the x's, okay? And now in equation 5, I've introduced a new variable in the source function. And so we can anticipate that the solution G will also depend on this new variable x prime, okay? But this seems odd a bit to start. But if I add a new variable on the right-hand side, we can expect that this new variable should also be on the left-hand side, okay? Now, having clarified this, we introduce this new coordinate system where I'm changing variable to r. R is x minus x prime. So it's the difference between where I'm evaluating the solution and this new variable x prime. So the Laplacian stays the same. I mean, if I calculate, you know, when if this is a constant, since I'm differentiating on the x's, the Laplacian stays the same. So we can rewrite equation 5 in this coordinate system like equation 6. If we are away from the origin, then the right-hand side is 0. And this is really easy to solve. We just need oscillating exponentials. When we turn, you know, including the Laplacian in spherical coordinates, we get this R factor here. And if we are away from the origin, then the solution is simply this oscillating exponential. The general solution then is given by this superposition A with plus IKR plus B exponential minus IKR, okay? And taking into account the specific case of k equals 0, we have eventually that the general solution to equation 6 can be written as this green function, which is the sum of the plus term, this one, and plus the minus one, G minus, which is this one. And now I've got, which I've written in this compact form, like with a plus and minus here. Now we need A plus B equals to 1 because of the k equals 0 term, okay? So I'm going a little bit fast, but you can imagine that this is all straightforward. Okay, I'm not using anything too fancy here. Just the solutions to the Poisson equation when we are away from the origin. Now, when we are at the origin, then this diverges, of course. Okay, but we can remember that this is again like the Poisson equation. Okay, so this would be, let me see, similar to the case of a point source when we have nabla cross phi equals I think it's minus rho over epsilon 0 from memory. And so a point source would be something like that, right? This would be a point source at the origin, okay? And so nabla cross phi for a point source, and let me write it with a circle like this, okay? Must be equal to q minus q over epsilon 0 times delta, okay? But we know the solution for the field of a point source, and it's simply that. Okay, so this is the Coulomb law. We know the solution for a point source. And so we have a representation of the delta function, which is 1 over 4 pi r equals to minus delta x, or this thing. Okay, so that's why when we have k equals 0, this oscillating exponential is 1, and the solutions are 1 over r, just like for the point source at the origin. Okay, so this is a representation of the delta function, and we're happy to have solved equation 5. Okay, now we'll be taking one step further, and we are going to extend the original problem to a time-varying source function. Okay, so going back, what we did here is we have equation 1, which is the wave equation we're trying to solve, and the source function depends on position and time. Okay, and then we propose to solve this equation in the Fourier domain, and we reached the Helmholtz equation. To solve it, I'm suggesting we follow this strategy, which is to introduce a different equation, which is the equation for the green function, where the right-hand side is a delta function. Okay, and this will be very useful, as we'll see very shortly. Okay, and the solution to equation 5 is what we just saw. Basically, what's here. Okay, these are the solution in changing variables to r equals x minus x prime. And now I want to further extend equation 5 for including a time dependence here, because we had a time dependence in the potential time dependence in the source function too. Okay, and so this is what I do. I extend equation 5. This is equation 5 here. Okay, well, let me perhaps write it down. Okay, so this is equation 5, and now we are extending the same equation, but to include a time dependence on the right-hand side. So equation 8 is the same equation, but written in real space. And equation 9 is the corresponding Fourier transform. So maybe I just want to go back one more time to help you see this. This is equation 1. Okay, and we are solving it in the Fourier domain. So look, compare equation 1 and equation 4. Okay, so this equation 4 is the Fourier transform of the equation 1, and we this second time derivative injects this k squared using the oscillating exponential. Okay, Now here we're doing the same. This k squared comes from this second derivative. I forgot the type here. But now I'm generalizing this equation. So this is a new equation I'm trying to solve here. It's equation 8 is similar to what I've got written here, but in the right hand side I've included a delta term on time. Okay, so we expect the green function to be dependent on position, but since I'm including a time dependence in the source function, in the source term, then the green function should also depend on time. And since I've also added a new time variable, t prime, well, this should also be on the left-hand side. So we have 4 variables for the green function, okay? Now, in the Fourier domain, this delta function is really simple. Now, if I take the Fourier transform of this part, are we taking the Fourier transform in time? And so the Fourier transform in time of this term of the delta is just the oscillating exponential, right? I mean, if I take the Fourier transform of a spike, it's going to give me an oscillating exponential, okay? So you can see that the right-hand side is simply the Fourier transform of what's above. And what's on the left-hand side is the same as always. This is the green function, but where we have gone back to this Fourier transform of the green function for one spectral component k, instead of having the time dependence here, okay? So I don't expect you to be able to reproduce this by heart. I just want you to follow the reasoning, okay? And see that we can actually find a solution to these wave equations fairly easily, okay? So we have just seen the solutions to this equation. How so? Because I mean, we have the previous equation we're looking at on the right-hand side here. Look at the Fourier version of this of the green equation. Now compare it with equation 9. I just have to multiply on both sides. I just have to inject here ei omega t prime. So I multiply both sides by the same oscillating exponential, and then I've got the solution. The solution is just gk times e to I omega t prime. Okay, so this is what I'm trying to say. We know the solution. And then going back to the time domain, we have finally the solutions for the green equation. Okay, so we have the functions that fulfill this delta function here. Okay, so we have this okay. Yes, so we have well, I think there's a little bit of algebra here which is hidden, but I'm taking the inverse transform of this quantity to go back to time domain, because time domain is hidden here in omega. So I need to integrate over frequencies and multiply by I omega t. And including this other t prime here gives me this tau where we have t minus t prime. So a bit of algebra is hidden here, but this quantity is just the inverse transform of the previous one, of the above one here. Okay, if omega and k are related with a simple dispersion relationship, so this would be in vacuum, so away from the sources or away from the radiating medium, then this r goes out of the integral, and we have this integral in omega of an oscillating exponential, which is a delta function. So long story short, we have the solution 10. Okay, so let's write it down, because I know that probably you're a little bit lost by now, but look at how this works now. we've got the required machinery. So we have, first of all, we want to solve equation 1. So let me write down equation 1. Okay, I've already I've put it in those terms. So I need to remember, okay, it's phi, and so we have, this is our master equation if you want. Nabla squared phi minus 1 over c squared d squared psi dt squared is minus 4 pi and the source term. This is what we're trying to solve. And then we solve this equation. We solved Nabla squared g. So let me bring it up again. Where did I put it? Here. So Nabla squared g minus 1 over c squared d2 dt squared g is minus 4 pi delta in x and delta in t minus t prime. Okay, good. And we've got the solution. This is it. Okay, so we know what the solution is for equation for the green function. Okay. And now what I'm trying to say is this, is that then if I've got g, I've got the solution for the first equation, because phi is going, yes, phi, let me put the time dependence. Position and time is then the integral over dt3x prime, the integral of dt prime of g times the source function. Okay, so how do we know this? Well, because if I apply, look at the first equation right on top of my sheet here. So I apply this operator to this version of phi. Okay, so we have that Nabla squared phi minus 1 over c squared d2 phi dt squared. So this would be the left-hand side operator, the wave D'Alembertian operator, okay? And this is acting on the x's and on the t. So not on x prime and not on t prime. So it goes inside the integral here. And we have this same D'Alembertian operator acting on g. So that would be a symbol for the D'Alembertian. And this source term is left untouched because it depends on the other variables. Now, this is the D'Alembertian here. This is what we call D'Alembertian of g. And this yields these delta functions. So on the right-hand side, we have the integral of dt d3x prime dt prime of minus 4 pi, the delta function in x minus x prime, times the delta function in t minus t prime. Okay, and that times the source term. Now this is trivial. We see that the integral in space goes away with this delta in space. The integral in time goes away with the delta in time, and this is simply minus 4 pi f. So we started off in a rather abstract and academic way, trying to look for the solutions of the green equation, apparently unrelated to the wave equation. But we see now that once we've got the solutions to this green equation, so if we have g, then we have all the solutions to the original equation, because we only need to integrate. What's written here, or equation 11, is the general solution to any wave equation with a source term. So we've solved the problem. We've solved the problem of radiation using the green formalism. Okay. Now, let's try and look at these plus and minus cases now. So this is, for now, the general solution. We have G for this generalized green equation for the wave equation with source terms. And accordingly, we have the solution. we have, let's see these plus and minus cases. Now, the plus case. So the solution with a plus, because there were two possible solutions for the green equation. Okay, so what
Professor?
See?
So in this case, we are solving this equation for phi, but in our case, phi is the electric field or the potential of the, or what is phi in our analysis?
Okay, so phi in here is either a component of the of the magnetic potential, of the vector potential, or the electric field, or one component of the electric field, or one component of the magnetic field. It's a generic way to, in a generic way, we write it like this. Where did I put this? Okay, there we go. So that would, equation one is what we're trying to solve, where phi really is either any components of this one or of phi, and it just depends on what source term we're using. So which source term is which is what we saw in the last chapter. So in the last chapter, we started off with remembering the Maxwell equation, and we wrote down the wave equation for each of those cases. Okay, so in the case of the electric field, sorry, in the case of the electric potential, the source term is just rho. And for A, the source term is just the current density. For the electric and magnetic field, the source term is a bit more complicated. Okay, so this is the general solution, but we have these two cases, plus and minus. Now this is tricky. Let me see if I can remember this correctly. Okay. So let's write down the plus solution. Okay, so we have psi plus at point x and t. So that would give us the solution in space and time due to some source function. Okay, and this is according to equation 11, it's an integral over x prime and an integral over dt prime of what? Of 1 over x minus x prime times delta t prime minus what goes here? Oh, if I got the plus in G, then I need to have a minus here. X minus x prime over C. Oh, and of course, we must include here the source function. So let's focus, for instance, that's a good idea actually. Let's focus on the electric field. We'll be replacing this generic phi by the electric field. Okay, and in this case, what goes here is, from memory, is going to be the charge density. And I think, yeah, that's just like that. It might be with a 4 pi in the denominator. Okay, and this is the source function in the primes. Okay, so this would be like, I'm particularizing to the case where psi is the electric field, just to focus ideas. Okay. All right. So yes. How can I explain this? This was yes. So we have to okay. So suppose that we are looking at we have the sources here in this time, in this region of space. So here we have x prime and t prime, okay? And we are calculating the field outside here, phi in x and t. Okay, so this is x, okay? So if we are considering a point here inside the sources, this would be x minus x prime, right? And this term here would be the time that light takes to connect those 2 points in space, okay? So this would be the light travel time, this term here. So what this delta function is telling us is that the plus solution needs to be retarded in the sense that the delta function, when I carry out this this integral, well, the delta function helps a lot because then I'm evaluating the sources, but at this different t prime, right? So when I carry out this this integral, this term here needs to be evaluated at t prime equals t minus this light travel time, which would be r divided by c. Okay, where r is this difference. Okay, so the plus solution with a minus here depends on the potentials when we correct for the light travel time. So this is the physical interpretation. Okay, the math is straightforward. All the green formalism has no physics. It's just pure math, basically. Now, if we want to do physics, you know, then we notice that the plus solution corresponds to this, that when we are evaluating the fields away from the sources, then I need to perform this integral over the sources, but in their retarded position. Okay, this makes a lot of sense. It means that whatever potential you can measure here depends on the position of the sources at the retarded time. This I'm sure you've heard of. Okay, but it comes straightforward from the math. And makes a lot of physical sense once we look at those specific solutions. Okay, so just to repeat, we have we want to calculate the fields at some point in space. What the solution's general solution tells us is that we need to evaluate the charges at the retarded time. So we can write it down like this. We can write down so. Is then the integral over dt x3 prime of rho divided by x minus x prime, but we are going to make this symbol here with a retard, meaning that we have to evaluate this at t prime equals to t minus x prime divided by c. And so, well, this is quite logical. So in the sense that if we have sources moving around here, each of them is going to be producing this Coulomb field, and the superposition of those fields at some point in space is the resulting potential. But this resulting potential needs to be calculated with the sources at the position they were to allow for the time travel for the light to connect the sources and the measurement points. Okay, so this is the physical interpretation, but we don't need to put this by hand. This comes directly from the math. Okay, and what's the opposite solution? Well, the opposite solution, it would be not the retarded solution, but the anticipated solution, and this would be what we need to do when we have. It would be the opposite situation when we are given this this electric field, and we want to figure out what the sources are that are producing this electric field. Okay. Now, I can't remember why I'm talking about this initial condition time before the sources are activated, or I need to refresh my memory a little bit about why I'm talking about these sources being activated and deactivated. But I think that you followed me so far about the retarded potential, the retarded case, which is the one that we'll be needing to calculate the fields caused by moving charges. Okay. I ask you to please give me a few days, so till Thursday, to refresh my memory and go back to this point, which is really important. The rest of this chapter is a lot easier, and it's just the application of what we've just seen. Basically, we use this generic form where we want to calculate the impact of well, we are assuming that we have sources, they jiggle and move. We have charges that are accelerated, currents, that time variable currents, and they generate fields. And we want to calculate those fields. Okay, so in this case, we use the retarded solution, written in compact form this way. Okay, so basically this notation, which is what I've just written here too, means to evaluate the sources at this t prime time given by this relation. Okay, it depends then on the point inside where in space where we're integrating. Okay, so we apply this generic formula to the electric field and the potential vector. Okay, and we can calculate the associated electric and magnetic fields using the standard formula, or we can use those source functions. So Felipe, these are the source functions for the electric and magnetic field. Okay, you can either using the green function or use these formulas, you get the same result. Okay, so it works. And you can, and this is tedious, it's done in Jackson, write down the final expressions for the electric and the magnetic field. So even though the electric potential and the vector potential have got simple expressions, the expressions for the electromagnetic fields are a lot worse. Okay, but we can approximate these solutions using multipolar radiation. And to do so, we go back to this idea of monochromatic components. So we Fourier decompose the source terms, so the electric current and the charge density. We have that the generic solution for the retarded potentials for the electric for the vector potential is just written in this standard way. But if we have oscillating harmonic sources, so if we do the Fourier decomposition of the source terms, then this oscillating exponential goes outside the integral here, and we're just left with this time dependence, the special dependence here in the integral. So we apply the Maxwell equations and distinguish these radiation zones. So I think the only one that's really important to us is the far zone. The intermediate zone, when we let me make a drawing of what I mean here. So this would be the sources. Well, I've got them here too. So this is where we have the sources. And this is where I'm evaluating we have D would be the maximum, this would be D. So we have the typical size which contains all the sources. So we are assuming that the sources are all concentrated in some region, okay? And this is, and then we're placing the origin somewhere inside the sources, important, okay? So R is like big R, almost. So we have to distinguish these three zones of interest. So if in the near zone, so if we have this case where both D is less than R, so we are here, okay? But these two are smaller than the wavelength, okay? Where the wavelength lambda is the speed of light times tau, the period, okay? So that would be C over 2 pi omega, I think. And omega is omega is this oscillating sources term, okay? So in the near zone, then this oscillating exponential is essentially 1 because k is 2 pi over lambda, and x minus x prime are both much less than 1. So much less than lambda, I mean, because of this request, okay? So we are in the near zone. And in this case, if this oscillating exponential is 1, look at what's here in equation 24. If this oscillating exponential is just 1, then this is beautifully just the Biot and Savart law, where we have that the vector potential is just the same as the magnetostatic case, modulated by this oscillating exponential. So if we are in the near case, we have, if we are in the near zone, very close to the sources, and at a distance that is less than lambda, so if the sources oscillate slowly, if the sources are oscillating slowly, then the fields oscillate in response as if in any instant the case was static, okay? Now this is one limiting case. The intermediate zone is hell. We don't want to look at the intermediate zone. People who work in antenna theory and do electric communications have to deal with this intermediate zone, and luckily we do not today. In the far zone is when we actually have the emission mechanisms for astrophysics. Okay, so we're very far away from the sources. And it is the opposite case where we are measuring the impact of the fields very far away from the sources, light years away, and much larger distances than the wavelength. Okay, but well, my hour has ended, so we'll be looking at the expression for the radiation zone on Thursday. On Thursday, then I hope to have finished this chapter. I'll go back to the retarded and anticipated solutions. I need to refresh my memory a little bit there. And so we'll finish with the Larmor formula and some applications. And from memory, these applications are, yes, so these are fairly important applications. I need you to tell me, because I think that semester has ended, and we are extending the course beyond the end of the semester. I'm happy to go into next week, but I'm not sure if you are. So I need you to tell me if you can, or if you're going on holidays or.
At least I don't know the calendar of the semester. I don't know in what week we are now. But I don't have a problem. So if you want to extend, for me it's okay.
Okay, thanks, Andres.
Same here, Professor. No issue with extension.
Okay,
Yes, Professor, we can extend, no problem.
okay, so then
Uh,
we'll extend the course into next week. Okay, Felipe?
No, I was going to ask if we're going to extend the course one more week, then we will still have time if we needed an exam, right?
Yes, of course. I made a mistake in sending the first partial exam too early. I think that so too late. It's all going to be accumulated at the end of the semester, but there is not much more we can cover, unfortunately. But I need you to help me here because I need to go fast. So I need you to work intensely today and tomorrow, and please prepare these applications from the textbook. Okay. So please have a go through, have a look at my summary or the textbook. Okay. And try to prepare these applications for Thursday. So it shouldn't take me too much time to go through multipolar radiation and the Larmor formula. And hopefully by the end of Thursday, we'll have finished chapter 3, okay?
Professor, I checked cursos and the semester end this week.
Yes, thanks, Andres. Probably it does. So that's why next week would be an extension. Okay, so let's try to do this on Thursday. Well, we'll do, this is a difficult situation and it's an exceptional one, and we do what we can. So thank you very much for attending today and see you Thursday then. Ciao.
Ciao, ciao.